This video is on the N-channel junction field effect transistor, and we'll start with structure. An N-channel JFET is pretty much just a compressed N-type resistor. So what we have here is that basically we have an N-type region here, which is the one for the resistor, and it's compressed because we have a P-type region on the top, this one here, that compresses the height of the resistor, and that P-type region compresses it against another P-type region on the bottom. The length of the resistor is basically the length of the compressed resistor, which is from one edge of that top P-type region to the other edge, and we call that basically the channel length. Then to contact one end of the resistor, we use a highly doped N+ region, and the other end with a highly doped N+ region. The resistance from that region to the edge of the compressed resistor, or the resistances rather, are low because they're uncompressed. So let's talk about biasing. First thing we're going to do is we're going to reverse bias the gates, and by the gates what I mean basically are the regions that here that compress the N-type region. So this is the top gate, this is the bottom gate. So if we look at this new graph here, what we see here is that we're going to tie the top gate to the bottom gate, and we're going to apply a gate voltage that is less than 0 to reverse bias the PN junction that results. When we have that, we establish here a depletion region between the top gate and the N channel, and the bottom gate and the N channel. Now we're going to take the voltage on the right hand side, we're going to call that the drain voltage here, and then on the left hand side the source voltage. And for now we're going to say that those voltages are about the same, so the device looks very symmetrical. So when we look at the resistance, first one thing that we're going to note here is that we're applying a negative gate voltage, but the negative gate voltage is not going to be so much so as to expand, because with a greater negative voltage it expands the depletion region here, and we don't want to expand the depletion regions to the point where it completely covers the channel and basically blocks the channel. So we're going to apply a negative voltage that is not so negative so as to pinch the channel. So we call this the pinch-off voltage. So it's negative but not as negative as a pinch-off voltage, and this pinch-off voltage is a negative voltage which could be negative 5 volts or negative 10 volts. It depends on the device. So now when we look at the resulting resistance, the resistance increases when the length of the channel is longer. It decreases when the width is wider. So what we see here, the width is basically the distance into the screen. And then we have a baseline conductivity of the N-type channel. And the higher the conductivity, the lower the resistance. And if we remove markers here so that we can declutter the screen, this gate voltage, if we increase that gate voltage, basically make it less negative, we take this depletion region and we basically contract it a little bit, and that decreases resistance. So that's why here we have this gate source voltage. The higher the gate source voltage, or rather the less negative, the lower the resistance. But now if that gate source voltage is so negative that it reaches the pinch-off level, basically this whole term becomes 0, then there's no channel anymore and the resistance goes to infinity. So that's why it's VGS minus VP there. So let us remove markers again to declutter the screen, and we're going to combine VGS and VP. Now remember, VGS is just the gate voltage minus the source voltage. So if we look at VGS, P is the gate source voltage minus the pinch-off voltage. That combined, we call it the gate drive. And gate drive, because the higher this voltage, the lower the resistance, and the higher the driving current. But we can do another combination. We can combine this baseline conductivity and this gate drive, and what we have here as a result is what we'll call sheet resistance. Sheet resistance is useful in design because it refers to the resistance of a single square of a particular material. And if we have 10 squares, then we have 10 times that resistance. So if we look here and we see that the length is 10 times the width, that's 10 squares, then we have 10 times the resistance. So sheet resistance is very useful in describing the resistance of a material independent of geometry, and then geometry can let us know what the actual resistance is. Okay, we're going to take this one step further and we're going to reverse bias the drain terminal. In other words, we take this region here, which is N plus, and we're going to raise that voltage and make it greater than 0. In reverse biasing that terminal, what we see here is that the depletion regions on that side will expand. So they will compress the resistor on this end slightly more than it's compressed on the other end here. So when we look at what we're doing here, what we're basically doing is we have a resistor here, and we can do it this way. Suppose we ground this side, we're applying a voltage across that resistor. So the current through that resistor is basically the voltage over the resistance. So we can do that fairly straightforward. We can keep the voltage there. And let me remove markers and start over so that we can declutter the screen. So first we have the drain voltage, and then we can incorporate the channel resistance that we just talked about. So the length to width becomes the width to length ratio. Then we have the baseline conductivity, the gate source voltage, and the pinch-off voltage appear on the other side. But here we have a new term. And what we see here is since we've expanded the depletion region on the right-hand side, on both sides here, we've compressed the resistor slightly. That means that the resistance increases and the current decreases. So this is a correction factor, or a correcting term, and it decreases the effective current when we increase that drain source voltage. But to put it into perspective, we're actually affecting half the channel, basically the channel that is on the right hand side. So that drain source voltage further reverse biases that half of the channel. So basically we can look at it in other ways, is that this reverse biasing action here since it's affecting half the channel, it's like it's half that voltage that is being reinforced. Again, let me remove the markers to declutter the screen. So this drains, let me do it again. This drain source voltage here, it affects half the channel, so its effect over the total channel is half of that voltage. And it basically it reduces the current. Okay, this is what we call the triode region, and it's called the triode region because the drain current is sensitive to drain voltage, drain source voltage, and also sensitive to gate source voltage. Let us now talk about saturation. So saturation is when we basically take the depletion regions on the drain side and pinch the depletion regions against one another. And that happens when the gate-drain junction is so reverse biased that it is even lower than the pinch-off voltage, is more negative than the pinch-off voltage. We can rearrange this a little bit to see it in a different perspective. This is gate voltage minus drain voltage, so we can add a drain voltage to both sides like this, and then we can subtract the pinch-off voltage from both sides. This removes it from this side, and we subtract the pinch-off voltage from this side. So what we have as a result is basically the drain voltage that is on the right hand side is greater than the gate's voltage minus the pinch-off voltage. Let me remove markers again so we can declutter it. So when the drain voltage with respect to the source is greater than the gate voltage with respect to the source and the pinch-off voltage, then we pinch the drain side of the channel. The pinch-off point is when the drain source voltage is just at this level, so that's what we're going to call VDS-SAT, the pinch-off point. So to see this more visually, we're going to apply a drain source voltage that is so high and it reverses the channel so much that it pinches both the depletion regions against one another. The pinch-off point is when it barely touches, and when we take the drain source voltage and we make it greater than that point, then the pinch-off point moves to the left here. And at that pinch-off point, it is basically when the drain source voltage, and this should be drain source voltage this way, when the drain source voltage reaches this VDS-SAT is basically the pinch-off level. So when we look at drain current, it's going to where it's basically the voltage across the resistor divided by the resistance. Well, the length of the resistor now is basically that effective length, and that's the one that offers resistance, and the voltage across it is VDS-SAT, which is the pinch-off voltage. So the drain current is the pinch-off voltage divided by that resistance. So we can do the same thing as we did last time. We have the pinch-off voltage remains there. Let me remove some markers that appear. Pinch-off voltage remains there, and we replace the channel resistance. We have the width to length ratio, but in this case is the effective channel length. We still have baseline conductivity, gate source voltage, pinch-off voltage, and then the VDS correction factor, except that now the voltage across the resistor is VDS-SAT, the pinch-off voltage. Well, something interesting here is that VDS-SAT is just VGS minus VP. Let me remove markers because they come a little crazy here. VDS-SAT here is just VGS minus VP, which is the same as this one here. So 1 minus half is basically half, so that's what appears here, a half. We still have the baseline conductivity and the width. But then we also note VDS-SAT here is also VGS minus VP, so VDS-SAT into VGS minus VP is VGS minus VP squared. It introduces this quadratic term. Now, instead of using the effective channel length here, we're going to use the original channel length, which is the length across the top gate. But what we said here is that as we increase the drain source voltage, we compress the channel on one side and basically decrease the length and therefore decrease the resistance. So we're going to model that effect with this term here. So as we increase the drain source voltage, which decreases the resistance effectively and increases the current, this is a correction factor that when we look at drain current and we increase the drain source voltage, we're going to get a slight increase in current. Let me remove markers here. So this right here is a correction factor, and that lambda is a channel length modulation parameter because it models basically the effect of the changing length here. When the length changes, then we have modulation effects, but this modulation effect is usually a small fraction of the entire channel. So this can be maybe like 10% or 5% of the drain source voltage affects it. So what we're saying here, in saturation, the drain current is sensitive to gate source voltage, but it's largely insensitive to drain source voltage. It is slightly sensitive, and it's just because of channel length modulation. So we have an interesting opportunity here, and this is very useful in design. This VGS minus VP, that's just VDS SAT, and we can solve for this term with respect to current. This is useful in analog design because we define current when we design. So doing it with respect to current gives us a sense of VDS SAT right away. So to do that, then we combine terms. We move the width to length ratio to the left-hand side, the conductivity parameter to the left-hand side, the channel length modulation correction factor to the left-hand side, and then we take the square root on the left-hand side. And what we get is this. So here we see all the components, and it's the square root of twice the drain current into the width to length ratio, conductivity, baseline conductivity, and the channel length modulation correction. Okay, so in saturation, what we're saying again is that we have a drain current here. So this is the IV curve, and let me remove markers again. We have the drain current in saturation is largely insensitive to drain source voltage. As we change drain source voltage, it doesn't change much. But as we increase the gate source voltage, that drain current increases. When the drain source voltage then reaches VDS SAT and it crosses that saturation point, it enters the triode region. In the triode region, the current is sensitive to both the gate source voltages, but at that point is also very sensitive to the drain source voltage. Now, one thing that we'll note with this device is that with respect to the middle point, the structure is very symmetrical. So instead of increasing the drain voltage with respect to the source, what we can do is the opposite. Let's say we ground the drain and then we put a positive voltage on the source, and basically the whole operation is mirrored. And instead of the current going into the drain, now the current goes into the source and out of the drain. So what we're saying is that the current is in the negative direction, but everything behaves the same. So that's what in this graph, when the drain current is negative, we're describing that region. So we still have a saturation region where the current is largely insensitive to the source voltage in this case, but it's very sensitive to the gate voltage. And then we have a triode region where the current is both sensitive to the gate voltage and source voltage. Now the last thing we'll say here is something about the symbol, and let's remove markers to declutter the screen. So we note that this gate here is basically reverse biased against the channel, so it never conducts really. It shouldn't conduct. So it's, instead of being a diode, it's more like a capacitor. So that's why we have two parallel plates here. It's a capacitor. We still want to indicate that it's the capacitor because of a diode. So we have a diode, PN diode, into the channel. So the arrow looks into the channel, and that's why we have here an arrow that points into the channel, which is basically what's on the other side. And the channel, what it really is just a resistor, and that's this here. Okay, I'd like to draw my symbol so that current goes down, and we know that current then goes into the drain. So this is the drain terminal and comes out of the source. We call the source because it's the one that sources the electron carriers that travel across the resistor. And then the drain basically drains those charge carriers that are fed into the source. So this is the source terminal, this is the drain terminal, and the voltage across the resistor is the drain source voltage. So in closing, I'll just say this. A junction field effect transistor is nothing but a compressed resistor whose resistance is determined by how much voltage we apply to the gate. So it's like a faucet. The higher the gate voltage, the more conductivity we have, the more current or water that goes through this faucet. I hope this was helpful. Thanks for watching.